Suppose you're winding down things, taking the SAT, you're down to the last 5 questions. You've been kind of keeping a little mental tally as you go through, and you know, or at least you think, you want to get at least 3 out of the last 5 problems correct. So what's the chance of you doing that? Well, let's take a look at a few things about the SAT. The SAT has 5 choices, only 1 of which is correct, and 4 of which are incorrect. So the probability of a correct guess, assuming that you're just guessing, is your 1 out of 5. What about the probability of guessing wrong? So that's possibility 2. Guessing the answer to a question and getting it wrong. Well, we'll denote that with a W, wrong, and its probability is 4 out of 5. So you want to calculate that probability. And so what you have is this event. Probability of a correct guess, another correct guess, another correct guess, a wrong guess, and then another wrong guess. And you need to calculate that probability. And there's something that's going to help you out, because this is really a lot of simple events kind of smushed together. Now, if you guess correctly on the first one, does that help you guess correctly on the second one? No, it doesn't. Nor does guessing correctly on the second one help you guess correctly on the third one or get the last one wrong. So if that's all true, what kind of events are each of these guesses? Independent. Independent. Good. They're independent. And that's really nice, because if they're independent, then I can take this probability, which is really probability of C or C on the first guess, C on the second guess, and C on the third guess, and a W and a W. So you got all 5 guesses. I can take this probability and split it up because they are independent. So those probabilities work out like this. The probability of getting something wrong is 1 minus the probability of getting it right. So you got 4/5. So 16 out of, 3,125. Yeah, that's not sounding good. But that's not the end of the story. If you're taking this test, does it matter to you which ones you get right, which ones you get wrong, just as long as you get 3 right, the 3 right you're looking for? They can happen in any order. So the question for you then is, how many different ways are there that can happen? And this is kind of a nice little review chance for you. We want to calculate how many ways are there to have 3 correct guesses out of 5 possibilities. So how many different ways can that happen? Oh, fortunately you've got your Google Sheets open, right? Oh yeah. Yeah, so let's go to Google Sheets. What's the command I need to type in there to get that? Equals combin, right? Tell me how many different ways there are that I can do that. Now you got to type in the number n, which is 5, followed by the number x, which is 3. What number are you getting? 10. You should be getting 10. There's 10 different ways you could have 3 right and 2 wrong. And if you wanted to list them out, in this case, this is small enough that can happen, here's how it would be. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Those are all the 10 different ways that this can happen. It doesn't matter to you which one of those happen. So if you wanted to calculate the probability of 3 correct and 2 wrong, then what you're going to do is you're going to take that probability that we had above, probability of 3 right and 2 wrong, and multiply it by 10. So what you'll end up with It's a little bit better of a chance, 160 out of 3,125. So, I don't know, maybe around a 5% chance if you're just completely guessing. So, I wouldn't count on it. You know, I hope that you can do better than a 5% chance for yourself. But this is an example of something called a binomial random variable. BRV. Now there's certain things that qualify something as being a binomial random experiment and leading to a binomial random variable. A binomial random variable is when you're looking for X successes out of N trials. So X successes out of N trials. And there's a little bit more to it than just finding the number of successes out of so many trials. And that's what this stuff down here is all about. To be a binomial random variable, it needs to satisfy these things. First of all, you have to have a fixed number of trials. Typically speaking, that's N. The trials have to be independent of each other. That is, what happens with one trial has no effect on what happens with the other trial. There are two possible outcomes, success and failure. The probability of success is P. The probability of failure is the opposite. It's 1 minus P. Now, a lot of times we denote that with a Q. Okay. So probability of success and probability of failure, P and Q respectively. There are two outcomes, success or failure. Now those can be defined as needed, but there's just two possible outcomes. And from one trial to the next, the same probability of success applies. So all four of those things have to be in place. Now I wrote it this way intentionally. Does anyone see something about the things that a binomial random variable has to satisfy that might help you remember these requirements? You have to test and see if it fits, right? Fixed number of trials, independent, two sample or two possibilities, and same probability of success. So it's a nice little acronym for yourself that you can run through. Now, if you actually had to calculate this by hand on a calculator, here's what's called the binomial PDF or probability distribution function. It's n choose x, p to the x, and q to the n minus x. Or q, the probability of failure is 1 minus p. So that would be the actual formula that you would plug in. If you were programming Google Sheets for Google, then this would be the formula that you would use. Fortunately for you, Google Sheets has this programmed in, so does your graphing calculator, so you don't actually have to do that. We can instead just work on Google Sheets. All right, so let's do some probabilities based off of binomial random variables. Hopefully everyone's got the handout here. Let's look at it on this part right here. A little bit easier to see. We'll start with example A. And right now I just want to kind of get used to the calculation on Google Sheets for you. The format of that calculation is down at the bottom of your previous handout. So it's down here. So it's called binomial distribution. The number of successes that you're going to type in, that's your X. Number of trials, that's your N. Probability of success is P. So you're going to type in all those, and then you're going to type in the word false. And I'll describe what it means to this calculation when you type in the word true, but I tend to recommend that people just use false and not try and get too fancy. But if you're comfortable, we'll figure out what to do with the true option there. So for the first example, just to practice with this command, we're going to assume that we have a binomial distribution with n equal 3 trials. Probability of success is 0.3. And we want to find the probability of exactly one success in this trial. So maybe you're flipping some kind of a coin that's pretty biased, comes up heads only 30% of the times. You want to find the probability of getting 1 heads out of 3 flips. So for that, we're going to plug that into Google Sheets. The command is going to look like this: binom dist. First comes n. No, let's see. First comes x, which is 1, then n, which is 3. Probability of success is 0.3, and then I'll type in false. Let's see that on Google Sheets. And let's see. Okay, here, I'll just type it in anywhere. Equals binom dist. And by the time you get to the D, typing that in, you should be able to hit the tab key because it recognizes your command. And then you can type in all the numbers: 1, 3, 0.3, false. Are you guys getting 0.441? Is that working for you? Yeah? My Zoomers, thumbs up. Hermione? All right. Jordan, thank you. Okay. Let's try this in a little more extended version. So this one was 0.441. Assume that random guesses are made for 8 multiple choice questions on an SAT test. So basically you've got n equals 8 trials, each with a probability of success of 0.4. That's not right. Probability of success should be 0.2, but we're going to go with their modified version of 0.4. Find the probability that the correct number of answers is fewer than 4. So we want to find not that probability equals 4, that it's fewer than 4. Probability of x less than 4. Okay. Let's check first of all to see if this actually fits. Are there a fixed number of trials? Yes, there's n equals 8. Are they independent? Well, we kind of went through that with the last one, or actually our beginning example. What you guess on the first one doesn't necessarily give you a better chance of guessing correct on the next one, so they're independent. Are there 2 possible outcomes? Got it right or you got it wrong. Pretty simple. And the probability of success stays the same throughout the trials because the number of correct and incorrect answers for each question doesn't vary. So we're good here. We're going to approach this a little different. So one of the things that people forget when they do these types of problems is that one of your possibilities is 0, that you didn't get any right. It's very easy to forget that possibility, so let me just alert you to that. But let's start with calculating the probability that you get exactly none of these right. And I want to use this column here so that once I type in this first command, I can get the rest of them just by clicking and dragging. So we'll do this. Equals binom distribution. When it recognizes that D, hit the tab key. You want the number of successes to be this column. So let's collect column A, comma. How many trials were there? 8, comma. What's the probability of success? 0.4. What do I type after that? False. So that should be your command. Okay. So it looks like this. Press enter. Enter. There we go. So a little bit less than a 2% chance of getting them all wrong. So if you get them all wrong, that's some really bad guessing. But let's click and drag this all the way down. And you should get a probability distribution table that looks like this. Okay, not bad. But we wanted to find out the probability that there was less than 4 right. So that's this probability over here. How am I going to get that? Because this is, this is the probability that I got 0 right, 2 right, 7 right, 8 right. What do I want to do to get this probability here? How am I going to get that? Any of my Zoomers got an answer?
Would you add the probabilities for 0 through 3?
Yeah, very nice. You want to add up the probabilities of all of these, 0 through 3. So, okay, put a little closing parenthesis there. The sum from B13 to B16. Dylan, what'd you get?
All right.
Dylan, what you got?
Pick someone else.
How about Dylan?
0.9 or 0.5948.
Yeah, sounds good. 0.594806. So that's just the sum of all 3 of these. You can check that very nicely. If you click into the formula, it'll show you the cells that are active in this calculation. So you can do a nice visual inspection. Let's go over to here and calculate this, except I'm going to make a little change here. Let's do equals binomial distribution, and then I'll do x, comma 8, comma 0.4. This time I'm going to hit true. And on the first cell, you see it doesn't make a difference. All right, well, let's drag it all the way down. Can you figure out what's going on? What's it doing if I have that set to true as opposed to set to false? One thing I will point out, this number here seems to be kind of exactly this number here, doesn't it? Anyone figure it out? So what it's doing is it's adding up all the probabilities as we go. So the first one's the same because there's only one thing going on. But the second one is the sum of the first 2. And the third one is the sum of the first 3. The fourth one is the sum of the first 4. So it's adding these up as you go along. So that's the difference between true and false on that command. I don't necessarily recommend this. I mean, if you're comfortable with it, go for it. But most people, I think, would probably be better off sticking with false in this command and then just adding up what you want. You can do this one, directly with this command right here. Or you can do it, let's see, D13, what's wrong here? That'd be D16 is what I want. You can do it, directly or indirectly. It's still not giving me what I want, but it's up to you, how you want to do those. Any comments, any preference? What do you think you're going to use? Just out of curiosity. Do you use column A or is column B or column C? You're free to use whatever works for you. Let's move on down to example C here. One of the things you can expect from me on the quiz on Monday is to decide whether or not something's a binomial random variable. Let's look at this one and see if it is or isn't. Assume that when adults with smartphones are selected, 61% of them use them in meetings or classes except for their statistics class. All right, I might have ad-libbed a little something there. If 6 adult smartphone users are randomly selected, find the probability that exactly 3 of them use their smartphones in meetings or classes. So, okay, let's work through this. Let's see if it fits. Are there a fixed number of trials here? Fixed number of trials? Rianne? How many? 6. Good. So n equals 6. Good. Independent. There's a couple different answers I'm going to give about independent, but kind of a nice simple one is if you're selecting people at random, and I'm assuming that you're talking about within a state or the country, you know, what happens with one cell phone user is not really going to change what happens with another cell phone user. If they're just random, strangers, people don't know each other, those events are going to be independent. That's one take on this. Are there 2 outcomes? What are the 2 outcomes? Let me do that way.
They use a smartphone or they don't.
Yeah, they use it or they don't. Pretty simple. So 2 outcomes, we're good there. Is it the same probability of success throughout the trial? Well, I guess it technically depends on how you're doing the trial, but does it make sense to sample with replacement? If you're only looking at 6 people, are you going to look at the first one and put them back in the pool and take a chance at sampling them again? Probably not. So you might remember a while ago, sampling without replacement leads to what kind of events? They were dependent events. Sampling with replacement was independent events. But because our sample size is so small, you've got the 5% rule. If your sample size is less than 5% of your population, then you can treat the probabilities as being the same, and you could also treat the events as being independent. All right, a little bit heavy on that one, but the short answer is that this fits. So we want to calculate the probability that amongst our 6 users, exactly 3 of them use their smartphones in meetings or classes. So this is a binomial random variable. Let's bang out that probability. Oh, looks like I already got it there. X is 3, N is 6. Probability of success is 0.61. And in this case, you have to do false. There's no choice about it. If you did true, that would change things a lot. If you did true, then it's saying, oh, well, you could have X equals 0, 1, 2, or 3. So let's get rid of true. Just leave it with false. So you should get about 0.269. Are you guys able to get that off of your Google Sheets? If I had the command there, I hope that you took the time to erase it and get rid of it. And try typing it in again for yourself. As far as taking a test or a quiz, on the top of your test or quiz, or maybe on the back, I will give you the format of the command. So I'll give you something like this that was on our handout: number of successes, number of trials, probability of success, and then true or false, depending on which way you want to do things. But I will give you that command. You have to understand how to use it. Example D. So same thing, except they're changing up the probability a little bit. Probability is now 59%, and we're looking at 11 adults. We want the probability that fewer than 4 people use their smartphones in meetings or classes. So how's that going to change things? Here's all the things that can happen when you're looking at 11 users. This is still a binomial random variable. I want the probability that x is less than 4. So how are you going to work that? You got a couple possibilities. You can use the cumulative density function, or that is, you can use true here, do things that way, or you could use just the regular false and try and do a little addition. Either of them work, but what are you getting? How are you working on it? It's either column. There is one thing that's reassuring about our calculation here. What has to be true for all distributions? Some of that distribution has to be, all the probabilities in the distribution has to be 1. All these probabilities have to be between 0 and 1, and the total has to be 1. And that's what you see down here, so it's a nice way to double check your work. But, all right, some people at home, my Zoomers, throw in some things into the chat, my Roomers. What are you getting for that probability? Or what should I do to calculate this probability? Maddie? Okay, go ahead. Sum. Hermione, go ahead. Sum. Okay. You're getting a little feedback here. Sum of someone. Actually, B9 to B12. These three. Yeah, B9 to B12. All right. So that would be this. This is the cumulative probability. So if I did that column, all I would need to do is use this command right here. Notice that these two numbers are identical. So it's up to you, but yeah, the sum of these first 4. Perfect. Thank you. We're going to skip example E and jump down to example F because there's a little bit more here that I want to go through, and I don't want to run short on time here. So let's go down to example F. You can take a look back at example E at your leisure. It's already in Google Sheets for you. So a lot of times what I do is I take examples right out of your homework, and that's what I did in this case. Example F says, assume that different groups of couples use a particular method of gender selection and each couple gives birth to 1 baby. Let's see. Let me zoom over a little bit. The method is designed to increase the likelihood that each baby would be a girl, but assume that the method has no effect, so that the probability of a girl is 0.5. The group consists of 46 couples. Answer parts A through C below. So the first part is to find the mean and standard deviation of the number of girls in those 46 births. Okay, we've practiced calculating the mean before from a probability distribution. And fortunately for you, I've got a lot of that work done for us. Here's our P of X. Hopefully you remember how we calculate the mean. We did that just a little bit ago in section 5.1. The mean was the sum of X times P of X. That gives you your mu, or your mean. And if I do that here, well, I got to go all the way down to the bottom of this column, X times P of X. And, is there any way I could have anticipated that result? What is that saying? It's saying on average, 46 couples should expect how many girls? 23. Is that a big surprise? Does there seem like it could have done that a little bit faster than all this work? I mean, actually, you didn't do it, but I mean, this is a lot of work that goes into the X times P of X and sum it all up. That feels like a lot of work to get that. What would be a shortcut? If I had, 100 couples, what would you expect for the number of girls or boys in and amongst 100 couples?
50.
50. What'd you do to get that?
Divide by 2.
Divide by 2, multiply by 1/2, same thing. So the shortcut that you're using actually works for binomial random variables only. So for a binomial random variable with n and p, so n trials, probability of success is p, mu equals n times p. Oh, well, that's great. The only thing I don't like about this is that people want to use this everywhere. It only works for binomial probabilities. What's this symbol? Sigma squared. Variance. So the variance is n times p times q. What's q?
1 minus p.
Good, so 1 minus p. And if I want the standard deviation is just the square root of sigma squared, which is going to be the square root of n times p times 1 minus p, or n times p times q. So what's going to be the standard deviation then for the number of girls in this experiment? So let's take a look here. That's going to be the square root of n, which is 46, times the probability of success. Well, we're assuming it's 0.5. And if the probability of success is 0.5, what's the probability of failure?
5.
It's also 0.5. Okay. Now I'm going to do something a little fancy for myself here to make my life easier. I'm going to hit the store key and store that value in X. So if I want to do the range rule of thumb here, then I just made my life a little bit easier. You can easily do that on Google Sheets. What it says, use a range rule of thumb to find the values separating results that are significantly low or significantly high. What do I need to do to find the range rule of thumb? What values do I want?
Average minus
Average minus
9 standard deviation.
2 times the standard deviation, or in this case, 2x. Thanks, Kata. And then 23, which was the mean, plus 2x. Oh, there you go. You can also do that in Google Sheets. No harm, no foul doing it on Google Sheets. Same kind of thing. You see mu minus 2 times the standard deviation and mu plus 2 times the standard deviation. Either way, it gives us our marks, 16.217 to 29.782. Now those are the exact values. But can you have 16.2 baby girls? No. So practically speaking, where do these limits start at practically? Where does significantly low start at practically speaking?
16.
Yeah, 16, and significantly high
30.
is at 30. Good. So those are the first values that match either of those criteria, significantly high and significantly low. How about 33 then? What's that saying about 33? Is that significantly high? Yeah, absolutely. So it is significantly high, and that would suggest that the method is successful. You got that many. It's beyond what you would expect, even by luck. Let's move on down to example G. Based on a poll, 40% of adults believe in reincarnation. Okay. Assume that 4 adults are randomly selected. Find the indicated probability. Completes parts A through D below. What's the probability that exactly 3 adults believe in reincarnation? Well, I guess the first thing you need to do is see if this actually fits. And as one last reminder, I would expect a problem just to see if certain things satisfy the criteria for a binomial random variable. We have a fixed number of trials. Yeah, just 4 of them. Are they independent? Are they independent?
Yeah.
Yeah. I mean, if you're selecting people at random, what somebody believes or thinks or feels about reincarnation is going to be independent of somebody else. Are there 2 outcomes? Yeah, they either believe or don't. Now, the same probability of success, we get a yes, and that's by the 5% rule. Technically, when you're drawing without replacement, you get dependent events, the probabilities are going to change, but in this case, no, it's not going to change. All right, so we can get away with that. Let's run through these things. First, we want to calculate the probability that exactly 3 are selected, and then we want to find the probability that all of them believe in reincarnation, followed by at least 3, and then we can see if 4 adults are randomly selected, is 3 a significantly high number who believe in reincarnation? So those are all binomial probabilities. We can calculate them here. And I'll give you a moment to work on those. If you're watching this later, you can fast forward until I get rid of my pause button.
Next.
Try and do these A, B, and C on your own. Type in your own commands. Don't rely on the stuff that I may or may not have there for for example G. And help each other out too. I mean, if you're not getting somebody in your neighborhoods, lean over and say, hey, how'd you do that? These calculators came out. Yeah. But it still does virtually everything. Yeah.
This is what I got.
Unless you're taking a lot more. Yeah, that should take you a long way. I wouldn't mind.
Yeah.
So that was for existing. It's for existing.
Yeah, it depends on how you go about it.
I mean, it finds a probability.
So what has to happen for C?
Oh. I gotta add some.
There you go. Another student that likes to wear slippers to class.
I was late, so I didn't even have time for questions.
How my Zoomers doing? One's thumbs up, a couple thumbs up. All right, thank you, Elijah, Dallas. So let's look at a couple of these. The first one, want to find the probability of exactly 3. So for that, we can use a binomial probability function. On Google Sheets, it would look like this, equals binom distribution of 3, 4, 0.4, false. And let me zoom out a little bit there. And let's type that in here. Equals binom distribution 3, 4, 0.4, false. 0.53 or 0.1536. I'm gonna be lazy. The next part simply asks me what's the probability of exactly 4 people. I'm just gonna paste the same thing in there. I've got to change one thing to get part B. What do I have to change? Yeah, the 3 has to be a 4. So, okay. So 0.0256. The last one, again, I can avoid really having to do a lot by hand. What's the probability that at least 3 of the selected adults believe in reincarnation? What does that mean in terms of my calculation? What are we going to do here to get the probability of at least 3? X is greater than or equal to 3.
Some of the previous two.
Yeah, sum of the previous two. It's probability that X equals 3 or probability of X equal 4. I can split this up because these are mutually exclusive events. Either 3 or 4 happen. So I'm just going to add those two. So it's a plus. And the easy thing to do here is just to click the sum. Equals the sum of these two. Bam. All right. I don't think I want to take the time to do example D or part D of this. Basically, you'd have to do out the whole distribution. Actually, you know what? I don't know. You could do it actually pretty quickly. It's mu minus 2 sigma to mu plus 2 sigma. We don't have to go through all that messy stuff that we did back in section 5.1, because now we're working with a binomial distribution, and we can calculate mu pretty easily. It's just going to be n times p, so it's going to be 4 times 0.4, which is 1.6. Sigma is going to be the square root of 4 times 0.4. If 0.4 is your probability of success, what's the probability of failure? 0.6. So that one, I'm going to take out my calculator for. Of course, you can do that on Google Sheets. You know what? Let me do it on Google Sheets, just for grins. So I'll get, let's write here, sigma equals square root, SQRT, of 4 times 0.4 times 0.6. There's your sigma. The mean was 1.6. So if I want 2 standard deviations below and 2 standard deviations above, I can do that pretty easily. It's equal to, I'll click this one here, minus 2 times sigma, and then copy that, oops, copy that, paste it over here. No, that didn't work out too good. Move everything. So equals mu plus 2 times sigma. So is 4 adults an unusual observation? Yeah, because 4 is outside of the range of mu minus 2 sigma to mu plus 2 sigma, so it's unusually high. It'd be unusual to get 4 adults in this that all believed in reincarnation. Nice. Okay. All right, let's move to something different. Little off script here. And for this, I need a volunteer. It's going to have to be somebody in class. Volunteer. Nobody. Everyone's all of a sudden looking at a spot in the floor that looks really interesting.
I'll do it.
They'll do it? Who's, all right, Tilda. All right, here's what I need you to do. I need you to take this bag of M&Ms.
Eat it.
Well, you first got to count it, all right? So take this bag of M&Ms, sort it by color, count it, and I need the results. What we're going to do is we're going to treat each of these M&Ms as, you know, a different binomial experiment. So if you take a look at your Google Sheets, then scroll over to the left and click PM class. That's where we're at. Now it's kind of funny. There's two plants in amongst the Mars M&M Mars world that produced M&Ms. One of them is in Hackettstown, New Jersey, which is where ours comes from, and the other one is in Cleveland, Tennessee. Yeah, I didn't know that there was a Cleveland, Tennessee either. When I looked at Cleveland, I'm like, okay, well, TN? What? Whatever. Now the probabilities, according to M&Ms, the probabilities of these different colors are right here. Typically speaking, with those 1 1/4 ounce bags, you get 57 M&Ms, but ours may be different. We'll see how it goes. So when you get them all sorted, Matilda, let me know. What we're going to do is we're going to treat each of these as if they're a binomial random variable. We're going to calculate the expected value, the mean and standard deviation, and then we're going to calculate plus or minus 2 standard deviations and see did we get an unusual amount of a particular color or not. Now, I'll be honest, it's a little bit rare that we get a significant event because they're pretty good at mixing up their M&Ms. So whenever you're ready, tell me how many red ones there are.
4.
So 4. All right. How many orange?
7.
7. Yellow,
5.
5. Green,
14.
14.
Yeah.
Blue, a lot of blue.
21.
21. Wow, that's a lot. And how many brown ones?
4.
4. All right, so we got cheated. They only gave us 55. I want my money back. All right, so let's take a look at what happens here. So the N, the number of trials here, and we're regarding each of these as a different trial, but the number of trials is 55. If you got 4 M&Ms, well, the average that we would expect for this data would be a little bit over 7. The mean and standard deviation here and here. So 2 standard deviations below and 2 standard deviations above give you this range. 4 falls in this range, so it's not a significant event. How about the 7? So let's see here. Can I do this? Yeah, there we go. So let's move over to the 7. So it's probably not the 7, but the orange. So orange, not quite a significant event there because the range here for the orange was between 6 and 17, and we got 7. So no luck there. Yellows. Did we get a significant event on that?
No.
Nope. Green. Nope. Blue.
Yeah.
Let's see. 21. All right. Yeah, 21 falls outside that, so yay. Go blue. All right. And then 4 down here. No, 4. All right, but cool. We got a significant event. We got an unusually high number of blues. Cool. So pretty nice. My morning class didn't get so lucky. All their data was not significant. But an appreciation for your hard work, Matilda. You can eat the data.
Thank you.
All right. Awesome. Awesome. M&Ms are cool. M&Ms are a great little source of examples for statistics instruction. Let's see. Let's finish up with example I. And I think this goes back to experiments done by Gregory Mendel. Assume hybridization experiments are conducted with peas having the property that there's a 0.25 probability that a pea has green pods. Assume that the offspring peas are randomly selected in groups of 26. Complete parts A through C below. All right. Find the mean and standard deviation for the number of peas with green pods in groups of 26. Okay. So let's work on that one. Before I get really busy to work, what should I check first?
It fits.
Yeah, thank you. Check if it fits. So let's run through this. Are there a fixed number of trials? Yeah. 26 of them, right? So there's a fixed number of trials. Are they independent? Kind of hard to say here. I don't really know much about this. We're going to eventually have to assume that they are for sake of completion of this problem, but it's not a lot here that helps us decide if they are or they're not independent. I'm assuming that you pick them at random from some big pool, maybe with, lots of pods coming from different plants, but there's not much there. There are two outcomes, either green or not green. And then, is that probability the same throughout the trial? I guess we're going to assume so. But when we're done with this one, I'll give you a couple examples so we can practice whether or not some data fits. So we want to find the mean and standard deviation for the number of peas with green pods in groups of 26. All right. What are we going to do to calculate the mean? How are we going to get that? Yeah, n times p. Cool. Omar, what are n and p for us in this particular case?
It is 26, P is 0.25.
Excellent. So it should be about 4.5, I think. Let me just double check that.
6.
26 times 0.25. I said 4.5, 6.5, my bad. So 6.5. How about the standard deviation? Well, standard deviation is going to be the square root of n times p times q. Georges, what numbers should I fill in to do the standard deviation? Let's start with the easy part. What's n?
2.2.
N was 26. You're right. What's the probability of success?
0.25.
And if 0.25 is your probability of success, what's the probability of failure?
0.65.
Yeah, 0.75, right? It's just 1 minus the probability of success. Now, if you wanted to, you could always just, take this number times the probability of failure and then take the square root of that. I'll just put it all together in one calculation. I won't try and get fancy here. So it's going to be the square root of 26 times 0.25 times 0.75. So about 2.21 if we round it off to the nearest hundredth. When and where I care about exactly how you round off things, I'll specify it in the instructions, like round off to the nearest tenth or hundredth. But, tenth or hundredth is probably the minimum that I would be looking for. Use the range rule of thumbs to find values separating results that are significantly low or significantly high. So we can do that on the calculator or on Google Sheets. Since we're doing so much on Google Sheets, let me just go there. So there's our mean. Standard deviation was equals square root of 26 times 0.25 times 0.75 equals mu minus 2 times sigma, and this one equals mu plus 2 times sigma. Oops, I don't want to type in sigma. I got to actually click on this cell. So the exact numbers we get are 2.08 to 10.91. U minus 2 sigma, U plus 2 sigma. 2.08 to 2.08 to 10.92, we'll call it. For purposes of this experiment, though, what number of p's begins to separate the low, significantly low, and the significantly high?
2.
So significantly low starts at 2, significantly high starts at what?
11.
Starts at 11. Nice. Nice. Excellent. Comments or thoughts on this last one? What if, let's see, how many people are in the United States Senate?
100.
All right, so there's 100 people in the Senate. 13 of them are polled to see what color hair they have. Is that a binomial random variable?
No. There's more than 2 options.
Yeah, there's more than 2 options, right? So one of the binomial criteria is that there has to be just 2 options. There's actually something else that's wrong with this. I'm assuming that you're going to sample without replacement. And here, because our population is so small, n equals 100, our 5% rule doesn't kick in. Now, 5% of 100 is 5. So we can't assume that the probabilities stay the same or that we have independence when our sample size is bigger than 5. So you lose that. So there's a couple things wrong with something like this. Most notably is that it doesn't have 2 outcomes. Trying to think if there's another quick example I can give, something that breaks down there. Those are really the 2 things that I wanted to highlight. There's 2 things that typically go wrong. I mean, a lot of times you have a fixed number of trials, but where things break down is you lose independence or the same probability, or that you have the 2 outcomes. So watch out for both of those. Tahara?
Could you explain like this a little bit more? I'm like struggling.
Sure. So you're looking for the same probability of success throughout the trials. So, for instance, in the current Senate, there's 25 women serving in the Senate as of right now. 25 women. So that means 75 men. Suppose you sample 8 of them. You want to find the probability of, sampling and getting 4 women or something like that. You're going to sample 8. So you start thinking, is it a binomial random variable? Fixed, independent, etc. So we have fixed number of trials. There's 8 of them. But as to whether or not they're independent, we lose that, assuming we're sampling without replacement. Suppose you're trying to get, figure out how many women you have. At first, there's 25 out of 100. If we sample without replacement, Tahara, after we take out that first sample, assuming that we got a woman for the first one, how many are left? 24 out of 99. And then if you try and get a third one, it's 23 out of 98. What's happening to these probabilities? They're changing, right? And that's the short story, is they're not staying the same. Whereas if you're guessing on the SAT, there's a 4 out of 5 chance you get one wrong. And then if you guessed wrong or right on the previous one, it's not going to change the probability that you guess wrong or right again. So those probabilities in that kind of a case stay the same,
Okay.
whereas here they're changing. Now, you can get away with this as long as it satisfies the 5% rule. These probabilities aren't going to change too much, or at least noticeably, if your population is big enough or if your sample size is less than 5%. I mean, technically they do change, but not in a noticeable amount. So if you can use the 5% rule, great. But in this example of the US Senate, once you get past n = 5, these probabilities start to change enough that we're saying, okay, you've lost this and you've lost independence.
So S and I kind of like work together.
Yeah, S and I are certainly related when you're dealing with sampling a population. Yeah, but not every time. I mean, when you're talking about the SAT, S and I are just different. You still want independence. So with that example that we had with the 46 couples, you know, again, you have independence. What happens with one couple's baby and what happens with somebody else's are independent. And then they told you to assume the probability was 50% for the whole thing. So that would give you your same probability throughout the trial. So there's a couple ways you can arrive at that S, but a lot of times it's through the 5% rule when you're talking about surveys. That's how you typically get that 5%. Okay, that should do it. Anything else on this one? All right, let's put this one to bed.